Hi everyone, in this video we are going to start with a new section, and the first topic that we will talk about is called vector fields. Now from Calc 3, recall the idea of a vector function, and if you break down the words, you have vector and a function. So what is a vector function? Well, it's a regular old function. The only difference is that what you input in here and what you output are different types of things, right? So the output is a vector and the input is a bunch of scalars. Right? So for example, temperature in your room, oh sorry, that is not a vector function. Wind, wind, wind direction and speed on the globe. Right. So if you look at Earth, there are some websites which provide you these little arrow things which show how the wind is moving across the surface of the Earth. It could also be ocean currents, and that's a vector function, because what's happening is, suppose here's a point. If I plug in x, y, z, the coordinate, or you can think of it as latitude, longitude, if you think two dimension, into this function, then it's gonna give me, say, an arrow, and what this arrow contains is, say 45 miles per hour wind, and also some direction, so maybe it's 71° northwest, which is a vector. So anything that you can think of which consists of a function, or which is a function which takes a bunch of inputs, usually there would be coordinates, and gives you a vector. So basically gives you an arrow which has direction and it has magnitude. That's a vector function. Now, using the idea of vector function, we define something called a vector field. Let D be a set of points in R. So we don't read this as R squared, we read this as R2. R2 means a plane. So you can think of it, this is a number line, which is real numbers. This is another number line, real numbers. So there's two number lines, they're called R2. Similarly, if you're in 3-dimension, this is a number line, this is a number line, this is a number line. So this whole space is called R3. So you have R4, R5, R5, R6, so on. So R2 is a plane region. DB a set in R2, so some set. A vector field on R2 is a function f with an arrow on top to indicate that it's a vector function that assigns to each point xy in D a two-dimensional vector fxy. So essentially, a vector field is a vector function. Okay, but we define it separately because of the context in which it is used. Let's look at an example. Suppose I have f of xy given by xi cap. So if you look at this, just as when you studied functions, one way to visualize what a function looks like is to plot it for different inputs, right? So let's do the same. At the point 0, 0, my input is just 0, so there is no vector. At the point 1, 0, I have 1 I cap. At the point -1, 0, I have -1 I cap. At the point 2, 2, I have 2 I cap. At the point 2, 1, also I have 2 I cap. So what I can do is I can draw a rough diagram. Nothing happens at 0, right? What happens at 1, 0? At 1, 0, I have a vector of magnitude 1, which is pointing in the positive x direction. So that's my I cap vector. At -1, I have a magnitude 1 vector, but pointing in the negative direction. At 2, 2, I have a vector pointing parallel to x-axis and magnitude 2. And at 2, 1, also I have a vector of magnitude 2. So it means that what you have here is if you draw all these arrows, as you move to the right, you're going to have longer arrows because they will become 3. As you move to the left, same thing happens, but they're just going to be pointing the other way because you have a negative sign. So just as with functions, you get a graph with these kind of things. So at 0, there's going to, on this y-axis, there's going to be no arrows, but you will have like really small arrows going to the right here, like 0.1, a little bit longer, and so on. And this side in the opposite direction. So instead of having like a graph of stuff, you will have a bunch of arrows that you can draw in order to understand what the function is doing or what the vector field looks like. So that's the image of a vector field. Usually it will have like an I cap direction, a j cap direction, so x and y, but it need not. Like for example, the one that we just saw doesn't have anything in the y direction. And the notation, we drop the xy usually and just write it as p I cap and q j cap, where p and q themselves are like vector functions. Well, you don't need a vector sign, sorry. P and q are some functions of x and y. Let E be a subset of R3, so this is three-dimensional space now. A vector field on R3 is a function that assigns x, y, z to a vector fx. So the same vector field in 3-dimension will now have various stacks, right? So for example, we saw that it stacks this way. Oh, sorry. Now we have our xy plane is over here. So things are going to be slightly different, sorry. Let me fix that. Okay, so now we have, if we analyze this, what we notice is, for example, for any one yz, the yz could be anything, is I cap. And for any negative one yz, because it doesn't depend on yz, is negative I cap. And for any, say, 2yz, it's 2I cap, so twice as long. So the same thing is happening, but they're all directed in the x direction now. So which means, as long as I have my x coordinate here, this is what. And for different y coordinate, it's not going to change. So we have arrows on the y of length 1. And the same thing happens if I go up. So nothing changes in the z direction as well. And in fact, nothing changes in this whole z plane. So x equals 1, wherever we have this plane, we're just going to have an arrow of length 1. Right? All over x equals 1. These are all going to be the same. But if I move ahead, if I go in the negative direction, then I will have these negative arrows pointing all the way over there in 3-dimension now. Even below and all of that. And then if I go to x equals 2, there's going to be another arrow. So let me do one more diagram here. So if you think about it in terms of planes, right, y, x, z, so here's one. So you have a plane. This is the plane x equals 1, right? And then you have another plane which is x equals 2. So what you have is all along x equals 1, you will have size 1 arrow, then size 2 arrow, and then a size 3 arrow, and so on. So that's what the vector field looks like. Right? And in general, it will have an I, j, and k component. Some or all of it could be 0. So it could be it can be a combination of all of these things. So example again, like I said, the vector field showing San Francisco Bay wind patterns on a particular spring day. So you take coordinates and you can find a certain way of a motion, a direction, and you can analyze, and there's cycles we can find, there's pathways we can find. There's a lot of things that can be done with this. Let's look at one more example which says, describe the vector field given by negative y I cap plus x j cap by sketching some vectors. So first of all, just like with functions, right, we can take values of x, y, wrong color. So we can make a table. We take certain values of x, y, and figure out what the vector corresponds to it. Take more values of x, y, figure out more vectors corresponding to it. So let's say I take 1 0, a 2 2, a 3 0, negative 2 2, negative 2, negative 2, negative 3 0, 0 negative 1, 0 negative 3. So when I plug in 1 0, I get the vector. So this is, it inverts, right? So y becomes the x coordinate and negative 1. Oh, sorry, positive 1. The y inverts and becomes negative, y inverts and becomes negative, y inverts and becomes negative, y inverts becomes negative, x remains the same. So x and y get replaced in position, and y also becomes negative of what it is. And now once you have that information, I can plot this, right? So for example, the first one is 1 0. At 1 0, I now have a vector that's pointing upwards. So the point is 1 0, the vector is 0 1. So it's length 1 and it points up. Similarly at 2 2, I have negative 2 2. So 2 2 would be somewhere here. Here's a point, 2 2. Where does the vector point? It's negative x direction and then negative positive y. But it's longer, so it's pointing somewhere here. It's pointing towards the northwest. 3 comma 0, it points at 0 3. So 3 comma 0, there's a vector that's pointing straight up. 3 comma 0, this is the vector 0 3. This is the vector negative 2 2. So once you draw this, you're going to have a bunch of arrows if you take these points, and you will notice that you're like, oh, there's these arrows are kind of like going around and there's some crazy stuff happening. Is there a pattern that can be found? So you can draw all of these arrows, but you can never draw all of them, right? Just as with when you try to plot a parabola y equals x squared by putting in a bunch of points, you will get a bunch of points, but not maybe the overall shape. But there are some tricks that can be done in order to understand what might be happening. So one of the trick here is using dot product. So one of the trick here is, if I take the position vector, right, x, right? If I take this function f, what is this function? The vector function f in vector notation is negative y x. And if I dot this with xy, which is your position vector, what do you get? When you dot this with xy, the dot product becomes negative xy plus xy equals 0, which means they are perpendicular. Remember from Calc 3 that when a dot product is 0, it means the vectors are perpendicular, right? So this vector is perpendicular to the position vector xy. And what that ends up being is that there's a sort of a circular flow going on, because in a circle you have the tangent vector is always perpendicular to the sort of the position vector there, because at any point the position vector is kind of like the radius, and this is where f is pointing. So this is a circular field, because there's always a 90 degree between the radius and the tangent. So there are some things like this which you can find out. So I'll leave this as an extra credit. It's very simple, similar to the one we did before, where instead of xi cap, now you have a zk cap. One of the applications or use of this is gravitational field. So this is your gravitational field formula, and as you can see, this is pointing towards the object. So if you're here and there's another object here, the gravitational pull direction is going to be at the position of this object, right? So we'll end this video here, and extra credit / video participation, etc. You can send me a rough sketch of this. Again, really simple. It should take you less than 5 minutes. Just draw the picture, take a photo, and email it to me. That's all for this particular video. We will look at a special field called gradient fill in the next video.